Now we can use our normal distribution to find probabilities for x bar, or this is find probabilities for our possible sample means. So if we want to use our normal distribution to find probabilities for our sample mean, we just have to find our new mean and standard deviation for x bar. We used to have to do a longer process when we had tables, but it's pretty simple now. We just plug everything straight into our calculator. So remember, we found a new mean, or this is mu with x bar is our average for all of our possible sample means. And it's just going to be equal to mu, which is our mean for the original population. And our standard deviation for all the possible sample means is equal to your original standard deviation over the square root of it. Once you have your new mean and standard deviation, you just plug everything into your normal distribution on your calculator's normal. You can go back and look at section 4.5 to see how we did that. But we'll just be using our normal CDF function on our calculator. Now there is a condition to do this. We can only use the normal distribution to find probabilities for our sample mean if our original population is normally distributed or the sample size is large enough, meaning n is at least 30. Okay, so let's look at this example. The number of gypsy moths in a trap is discrete and very skewed. Okay, so discrete means like you can only have one moth or two or three. It's very skewed. It didn't say which direction is skewed, just that it's skewed. The population mean is 0.5. And the standard deviation equals 0.7. Those are for our original population individual values. And Paul checks 60 traps. Okay. So what's the distribution of x bar? Well, our shape will be normal because n was bigger than 30. And that does mean we can use the normal distribution now. Our mean will be, mu for x bar will just be equal to our original mean, which is 0.5. And our standard deviation, our sigma of x bar, will be equal to our original standard deviation over the square root of our sample size. So 0.7 over the square root of 60, which is 0.09036. So again, what is x bar? All of these values, this is for all the possible values of our sample mean. When I say all the possible values, it's because we haven't actually picked our sample yet, so we don't know what our sample mean will be. Our sample mean will change based on what sample we pick, but I do know all the possible values of our sample mean will be normally distributed. It will have a new mean of 0.5, and this distribution of all the possible sample means will have a standard deviation of 0.0936. So what's the probability that the number of moths is greater than 0.68? The mean number. So probability that x bar is greater than 0.68. So the average per trap is greater than 0.68. So I'm centered at my mean of 0.5. We're looking at 0.68. The probability greater than that. So I'm going to use my normal function. Okay, I'm going to do a lower bound of 0.68. An upper bound of like a billion or something, or million. I'm going to use my mean of 0.5 and my standard deviation. Make sure you use your mean and standard deviation of x bar. Of 0.09036. So I just put all that into my calculator. So let's go to my distribution. I have a normal CDF. My lower bound is supposed to be 0.68. I want my upper bound to be about a million or so. My mean is 0.5. My standard deviation is 0.09036. And this gives me 0.02318. So that's about the probability of getting an average of greater than 0.68. Let's suppose the time x between text messages arriving on your cell phone has a population mean of 25. So this is for our original. Mu equals 25 and our standard deviation equals 20. You record the times between your next 50 messages, and we're going to take a sample of 50 messages. So now we want to know about the sampling distribution of x bar. Okay. Now remember, this means all the possible values of x bar we could get. You can actually type in x bar. Okay, so first you want to know, well, what's the shape? Okay. So n is big, so it will be normal. Our mean for x bar is just equal to our original mean, so 25. And our standard deviation for x bar is equal to the original standard deviation over square root of n, so 20 over square root of 50 gives me 2.828. So what's the probability that the mean, or the average, that we happen to get? So we're going to take one sample. What's the probability that we happen to get a sample with a mean less than 28 minutes? So looking for the probability that x bar is less than 28. Okay. So here is my 28. I'm looking for this probability that's to the left of it. We're just going to put it in our calculator again. We'll use our normal function. Make sure you use mu of x bar and sigma of x bar for your mean and standard deviation. So we want our normal CDF. My lower bound is going to be negative 1 million. My upper bound is 28. My mean for sample means is 25. My standard deviation for the sample means is 2.828. And this probability is 0.8556. So there's about an 85% chance that I will happen to pick a sample that gives me a sample mean of less than 28. So there is a 85.56% chance that I will pick a sample that has a sample mean of 28 or less. So what's the probability that the total time between 50 text messages is 1300 minutes or greater? We haven't talked about total time, but we could figure this out, because if the total is 1300, then the x bar would just be our total divided by 50, which is 26. So we're looking for the probability that x bar is greater than 26, greater than or equal to. So here's my 26. I'm looking for the area to the right. Okay. Again, we'll use a normal CDF. Make sure you use our mean for x bar, standard deviation for x bar. So second, distribution, normal CDF. My lower bound is now 26. My upper bound is 1 million. Our mean, again, is 25, standard deviation 2.828. And this probability is 0.3618. So this means when I take a sample, there is a 36.18% chance that my sample will have a total of 1300 or more. Because, again, in advance, we don't know what values we'll get in our sample. This is saying before I take my sample, this is a chance that I'll have a total of 1300 or more. And what sample mean time between text messages would have a 0.30 probability to the right? So this is actually the reverse. We're saying we know that my area to the right is 0.30, which means the area to the left of 1 minus 0.3 would be 0.70. And we want to figure out what x value would divide it like this. So this means we have to do an inverse normal function. Okay. I can do an area of 0.3 to the right. If your calculator only does left, then do 0.7 to the left. So second distribution, inverse normal function. My area is 0.3. My mean is, make sure you use mu x bar, which is 0.5, and standard deviation for x bar, which is the 2.828. So my mean is 0.5, standard deviation 2.828. We want our right. So x bar, since that's what we're talking about is averages, is 1.983. Okay. So of all of the possible sample means that we could pick, about 30% of them will be higher than 1.98. So let me say that one more time. Of all the possible sample means we could get, about 30% of them will be higher than 1.98. You know, I was just realizing that seemed like a really low number. There's a good reason that's a really low number. My mean's not supposed to be 0.5. This is where we need a real class, so you guys can shout at me. It's supposed to be 25. That was the previous problem. Let's go back and fix that. Okay. So x bar is supposed to be 26.48. That makes a lot more sense. And finally, smaller standard deviations mean our estimates will be more accurate. Looking at our text messages again, how big of a sample would you need if you wanted to make sure that the standard deviation for your x bar is less than 2 minutes? Well, let's see. We know standard deviation for x bar is equal to our original standard deviation over square root of n. So if we want our standard deviation for x bar to be 2 minutes, and our original population has a standard deviation of 20 minutes, and we want to know our sample size, we just put in everything we know, so we still need our sample size, so we'll solve for n. So we'll have 2 times the square root of n equals 20, or square root of n divided by 2 equals 10, so n equals 100. And if you want to make sure it's less than or equal to 2, we'll just make this a greater than or equal to 100. And our last example here, and I'll do in the video, and the last one you can do on your own. Here's a right skewed population. The population mean is mu equals 10, population standard deviation is 8. So mu equals 10, sigma equals 8. We want to take a sample size of n equals 5 and look at our sample mean. Okay. So first of all, look at this distribution. This is not normal. This is very right skewed. And I want to know, can you use the normal distribution for this problem? Well, we can only use the normal distribution if it's normal or n is at least 30. Okay, but here n is small, and that is definitely not normal. So it's not normal. My sample size is not 30. So no, we can't use the normal distribution. So when I say what's the probability that the sample mean is greater than 11, I would say I can't do this. Okay, because the conditions are not met to use the normal distribution.